Professor Carlos Frank from Durham University has stated, "I've dedicated my entire career to developing a specific theory about the universe, and now this theory is being questioned. I embrace this challenge because it is through such questioning that we advance and make progress in science." The James Webb Space Telescope is fundamentally disrupting many long-held beliefs in cosmology that have been accepted as truth for a century. A new ultra-deep image has revealed that we have made errors in astronomy. The telescope, which was intended to reveal the first stars of the universe, is instead challenging the previous worldview and may introduce a completely new scientific paradigm. Not all researchers are apprehensive about these new findings. Many scientists are welcoming these developments because it has long been evident that there were issues with our previous theories. The inconsistencies in measuring the universe's expansion rate alone should have alerted researchers years ago. However, instead of correctly interpreting these warnings, many held on to outdated theories. The cosmic microwave background radiation, CMB, which is the oldest light in the universe, was created about 380,000 years after the Big Bang, when the universe had cooled sufficiently for electrons and protons to form stable hydrogen atoms. This transition, known as reionization, made the universe transparent to light. The CMB was first detected in 1964 by American physicists Arnold Penzias and Robert Wilson while they were working on new antenna technology. They encountered a persistent noise coming from every direction in the sky. This discovery was initially considered strong evidence for the Big Bang theory. Penzias and Wilson were awarded the Nobel Prize, and their finding became a cornerstone in the history of astrophysics. The CMB likely provides a snapshot of the early universe, with tiny temperature fluctuations offering critical insights into the conditions shortly after the Big Bang. Scientists use the CMB as a reliable imprint to measure fundamental aspects of the material cosmos, including the universe's expansion rate. Edwin Hubble had already made such calculations in the late 1920s. He observed that distant galaxies are moving away from us in all directions, and that their speed correlates with their distance, which is now known as the Hubble law or the Hubble constant. Although Hubble's measurements were groundbreaking, they were not as precise as the techniques developed later. When the CMB was discovered, researchers recalculated the expansion rate, finding it significantly lower than Hubble's initial estimate. Subsequent recalculations using type Ia supernovae as standard candles provided a more accurate measurement, but discrepancies remained. The difference in expansion rate measurements has been known since the 1990s. Researchers have suspected that there could be issues with the CMB data, measurement methods, or the concept of universal expansion. This discrepancy, known as the S8 tension or Hubble tension, indicates that our understanding of the universe might be fundamentally flawed. Since the James Webb Space Telescope began its operations, it has provided surprising data that could help clarify the issue. Galaxies so ancient and mature that their formation should theoretically predate the Big Bang are challenging old scientific theories. Astrophysics now faces what is considered the greatest crisis in modern astronomy. The expansion rate of the universe and the Big Bang theory are under scrutiny. Webb's images reveal a universe that differs significantly from past models. The S8 tension served as an initial warning, and researchers who still adhere to outdated theories now face a dilemma. Many scientists are grappling with the realization that our knowledge of the universe may be inadequate. This uncertainty has left many researchers troubled and confused. To address this crisis, we must understand how science operates. Theoretical scientists use a blend of mathematical models, empirical data, and deductive reasoning to draw conclusions. Their knowledge comes from observed phenomena, experimental results, and theoretical analysis. The term theory itself suggests constructs and ideas rather than absolute truths. Our practical knowledge derives from images provided by telescopes, sound waves, and radiation captured by radio telescopes, and data from neutrino and gravitational wave detectors. The James Webb Space Telescope allows us to break down the oldest light into individual frequencies and analyze it in unprecedented detail. It can show which elements were prevalent in galaxies over 13 billion years ago, the mass contained within them, and the number of stars present. However, Webb's images may have limitations. For instance, it cannot always distinguish between galaxies and black holes that emit similar brightness due to massive accretion disks. Our scientific understanding has evolved to accept many eventualities as truths and has often dismissed alternative explanations. New findings from the James Webb Telescope offer crucial clues that may lead to replacing old theories with new truths. Scientists are currently grappling with these revelations, which seem so extraordinary that finding new explanations is challenging. The latest discoveries are shaking the foundations of physics, causing concern among many researchers. Physics teachings today are still heavily influenced by Isaac Newton's 17th-century work. For 4 centuries, his laws of motion and gravity provided the foundation for understanding the physical world and the universe. Newton's laws explain object movements under everyday conditions effectively on Earth. However, in space, his ideas required expansion, largely accomplished by Albert Einstein in the early 20th century. Einstein's special theory of relativity, published in 1905, revolutionized the understanding of space and time, proving their relativity to the observer's motion. His general theory of relativity, published in 1915, extended these concepts with mathematical proofs of gravitational phenomena based on spacetime curvature caused by masses such as stars or galaxies. While Einstein's theories were coherent in many areas, he recognized their limitations and sought a unifying world formula without success. No researcher has yet succeeded in this endeavor. It is intriguing to consider where mistakes might lie. Michio Kaku, a prominent American astrophysicist, suggested that solving this problem could lead to a Nobel Prize. We need to investigate what facts scientists might have overlooked, whether there have been misinterpretations of phenomena, or if telescopes might be at fault. Dark matter and dark energy are top suspects in the cosmological crisis. Current models suggest that dark matter and dark energy together account for about 95% of the universe, but neither has been directly observed or proven to exist. They might not exist at all, or perhaps have properties we do not yet understand. One idea under discussion is that these dark components' properties may have evolved over time, potentially indicating some form of intelligence. Gravity, which is supposed to cause attraction through mass or spacetime curvature, has not been definitively proven. Although spacetime curvature ideas, largely from Einstein, have been validated numerous times, we cannot entirely rule out the possibility that gravity has different properties than we assumed or that another effect causes gravitational attraction. Over the decades, certain values in cosmology and astrophysics have been established as cosmic constants, believed to be largely reliable due to their stability. Calculations suggest that small variations in these constants could provide new insights into the universe and explain phenomena without dark energy. It is also possible that our interpretations of light's shift have been incorrect, leading to inaccurate distance measurements and galaxy ages. Perhaps our assumptions about the universe's initial conditions were flawed, or we misinterpreted the cosmic microwave background radiation. It might even be that the universe does not originate from a single starting point, challenging the Big Bang theory. Despite our technological advancements, minor errors in the Webb telescope or other observational tools cannot be ruled out. Engineers and scientists have acknowledged that errors in instrumentation, data processing, or interpretation are always possible. The ongoing reevaluation of cosmological theories underscores a fundamental aspect of scientific progress: the ability to adapt and evolve our understanding in light of new evidence. The James Webb Space Telescope's observations are more than just a technological leap. They represent a pivotal moment in our quest to decipher the universe's mysteries. As we grapple with these revelations, it's important to recognize the broader context and implications of such scientific advancements. In the realm of cosmology, the process of refining theories is often driven by the need to reconcile observations with theoretical models. The discovery of unexpected phenomena or inconsistencies in established theories can be unsettling, but it also presents a valuable opportunity for scientific growth. Theoretical models in cosmology are constructed to provide a coherent framework for understanding the universe's origins, structure, and evolution. However, as new data emerges, these models must be tested and, if necessary, revised to accommodate new insights. One significant area of focus is the concept of dark matter and dark energy, which are central to contemporary cosmological models. Dark matter, an invisible form of matter that does not emit or absorb light, was proposed to explain discrepancies between observed galaxy rotations and the mass predicted by visible matter alone. Similarly, dark energy was introduced to account for the observed accelerated expansion of the universe. Despite their crucial roles in current models, both dark matter and dark energy remain enigmatic. Efforts to directly detect dark matter through experiments on Earth have so far been unsuccessful, leading researchers to explore alternative theories and possibilities. The challenge of understanding dark matter and dark energy is compounded by the vast scale involved in cosmological studies. Observations of distant galaxies, cosmic microwave background radiation, and other astronomical phenomena provide indirect evidence of these components, but their nature remains elusive. This uncertainty has prompted scientists to consider a range of hypotheses, from modifications to existing theories to entirely new paradigms. For instance, some theories propose that dark matter could be composed of more exotic particles than previously thought, or that dark energy might be a manifestation of a new fundamental force. Another intriguing aspect of cosmological research is the study of cosmic inflation. This theory posits that the universe underwent a rapid expansion in its earliest moments, leading to the large-scale structure we observe today. While inflationary theory has successfully explained many features of the universe, such as its uniformity and flatness, it also introduces questions about the nature of the inflationary period itself. Recent observations that challenge established models of inflation could lead to revisions in our understanding of the universe's early history. Additionally, the search for extraterrestrial life continues to be a major driver of astronomical research. The discovery of exoplanets, planets orbiting stars outside our solar system, has opened up new possibilities for finding habitable worlds. The James Webb Space Telescope's ability to analyze exoplanet atmospheres for potential biosignatures, such as water vapor or oxygen, represents a significant step forward in this quest. The potential discovery of life beyond Earth would not only revolutionize our understanding of biology, but also have profound implications for our place in the universe. As we explore these frontiers of science, it's important to remain open to the possibility that our current models may need to be adjusted or even replaced. The history of science is replete with examples of theories that were once considered sacrosanct, only to be overturned by new evidence and insights. The ongoing dialogue between theory and observation is essential to the progress of scientific knowledge. In the context of cosmology, the journey toward understanding the universe is far from over. The challenges posed by new data from the James Webb Space Telescope and other cutting-edge instruments remind us that the pursuit of knowledge is an ongoing process. As we continue to refine our theories and explore new possibilities, we can be confident that each discovery brings us closer to a deeper understanding of the cosmos and our place within it.